Hey guys, welcome to another video in our Year 9 probability series. Now, you may have noticed that all of the previous videos we talked about here and some of the different tools we used for showing these probabilities and outcomes were all examples of looking at multiple events. So whether it's a coin being flipped 2 times or multiple letters being drawn out of a hat and looking at the probabilities of making something like that. We are doing the exact same thing here with tree diagrams. Now, all of these things we're talking about, you can just think of these as tools in your mathematical toolkit, and you're just going to be pulling out whatever works better for you, what looks nicer, what helps you best approach this problem, and using whatever we need as depending on what the question requires of us. Now, tree diagrams are a really good way of helping us to visualize certain bits of information, particularly these multi-outcome events. So these things being done more than once. So take a coin flip. So we have the first toss here, toss 1, and we have another toss here, toss 2. What a tree diagram does is it pretty much breaks up all of our possibilities, and it shows this nice little tree spanning out, which gives us all of the total possibilities and outcomes we're going to come across. So if I flip a coin, so we have this coin here, and I'm flipping that. When I flip this coin, I'm going to get 2 possible outcomes. I'm either going to get a head or I'm going to get a tail. So the first bit of my tree here is going to show my 2 possibilities. So my toss 1, I can either get a head or a tail. And now from my second toss, I'm going to get a possible heads or tails again. So whether I get a head first or a tail first, after this first flip, the chances are going to be I'm going to get a head or a tail after. So whether I get this head first, when I do my second flip, I'm going to get, once again, either a head or a tail. And if I've gotten a tail first, the possibilities are still the same. I either get a head or I get a tail. So I'm pretty much looking at 2 separate tosses and the possibilities that happen for each of those. Now, to construct a tree diagram, this particular example, you may notice, we talked about this last time. This is what we call an event that is with replacement. Now, remembering what I mean by that just means that after my first coin toss, my events don't change. I've got the same possibility of options after. It's not like I flip a coin once and once I get a head, I replace the head for the next toss. It doesn't work like that. This just means that once we do our first either flip of a coin or our first roll of a die, the second types of options and outcomes we're measuring are exactly the same as the first. There is no replacement. There is replacement happening in the sense that we replace the first toss with another identical one. Now, this will become a lot more clear when we look at this idea of without replacement in our next example. But just to consider this tree diagram now, let's write all of our outcomes on the right hand side. So I have the possibility of getting a head and a head, or getting a head first and a tail after that, the possibility of a tail first and then a head, and then a tail and a tail. So the same as our arrays for 2-step experiments video previously, something like flipping a coin, we're going to get the exact same outcomes. It's just a different way of showing the information. So our total number of outcomes here, we have 4. And once we have these, once we have everything drawn in our tree diagram, we can start to answer some probability questions. So the first is we want to find the probability of tossing 2 tails. So all we're going to do is we're going to count the number of favorable outcomes. So out of all of these outcomes, which ones show 2 tails being flipped? And we only see this one down the very end here. So that is going to become my numerator on my probability. And I'm going to do this over the total outcomes, all of the possible outcomes I can get. And as we've seen in our diagram, there are 4 possible outcomes here. So I have a probability of 1 out of 4, or a quarter, or 25%, however you want to think of this. Now, for part B, we want to find the probability of 1 tail. So the only times when we get 1 tail. Now, looking here, my first one has no tails. My last one has 2 tails. We don't want that either. We just want 1 tail. So I can see here and here are both outcomes in which I get exactly 1 tail. So this makes up 2 out of the possible 4 outcomes, which we can also write as 1/2 once simplified. Now for part C, our very last example, we want to find the probability of getting, this is where our language is important, at least 1 head. Okay, what do we mean by that? We've touched on this in the previous video, but I'll go over it again. At least 1 head implies that we can get the times when we get 1 head, or anything more than that. Remember, we are looking at least 1 head. So in other words, 1 or more heads. That is what our language here means. So if we count these up, I have these 2 options that I've already highlighted in which we get 1 head. We also have this option here in which we get 2, but that still falls under the umbrella, the category of at least 1 head. So here, to find this probability, I'm going to end up with, I should say, 3 favorable outcomes out of a possible 4. So out of these 4, tails, 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 heads, heads, tails, heads, heads, 3 of these make up the favorable outcome of at least 1 head. Now, let's look at our second question. And this is going to be tree diagrams without a replacement. Now let's look again at what we mean by that, because these are, on paper, look quite similar, but just the difference between with and without replacement actually ends up being quite significant. So, let's say 2 people are selected out of a group of 3 without replacement. So we have 2 people selected out of a group of 3. So, and this is without replacement. So, what we mean by that is, just say we have our 3 people here, 1, 2, 3. What without replacement means is that when we select one of these people, they get pulled out of the pool of outcomes we can have. So if we take this person out, when my second event comes along, we only have these two people to choose from. We're not factoring in this third person. Remember when we looked at with replacement, we looked at a coin toss. So once, for example, heads got selected up here, heads was still an option for my, heads was still an option for my second coin toss. So that is what with replacement means. We flip a coin, but then we reset it to a clean slate with heads and tails again. So I can choose from one of these two. Once this first one gets selected, it's still up for grabs in this as an outcome with the second toss. Now down here, once my person has been pulled out, I only have these two people to choose from. Now I'm going to leave this little diagram here, and we're going to just quickly write out the rest of this question. So from this group of three, we have Anna. We're going to write A for short. We have Brad, which we have B for short, and Chris, which we have C for short. Now, we want to, in part A, list all of the possible outcomes for the selection using a tree diagram. So, I have Anna, Brad, Chris. Now, I want to draw my tree diagram. So we want to first ask ourselves, when we come up with this tree diagram, how many options do I have to start off with? That'll tell us how many branches we have to draw. So I have three people here. So that means when I go and draw my tree diagram, I have 1, 2, 3 possible people to choose from. And this is like my first selection. This could be, people selected out of a room, for example. So this is my first selection, and my options are going to be Anna, Brad, and Chris. So where this gets tricky when we think about without replacement is we want to consider when each one of these events happens, this one, or this one, we want to look at how my outcomes change for the second selection. Let's write that up here. So second selection. Here we go. Selection. Okay, now let's visualize this here. If I pull Anna out here, she's been selected first. That is this branch of my tree here. That means I only have, for my second selection without replacement, Brad or Chris to choose from. So here I'm going to write that I can only pick Brad or Chris. Now, let's pop Anna back with the rest of them. Let's say Brad gets pulled out first this time. Now we are looking at this particular probability, or this particular outcome, I should say. So Brad has been pulled out first. Who is left to make up my second selection outcomes? Well, I can look at it on the diagram. I have Anna and Chris remaining. So here, I can only choose from Anna or Chris because we are not having any replacement happening. We're not putting here Brad back into the pool. He's been selected first under this first selection, and then this is without replacement. So we're not putting him back in. We only have Anna or Chris to choose from. And finally, let's pop Brad back in there, and we will pull Chris out. This is our last option for our first selection. So this is Chris getting pulled out, and hopefully you can see by now that for my second selection with replacement, I always have one less option than the 3 I have here. Because once I select Chris, I have Anna or Brad to choose from. I can see that up here. Now, let's pop these guys back in. So, in my first selection, I had 3 people to choose from. In my second selection, I had 2 people to choose from. Now that this is drawn, let's just list quickly. Give myself some more space. Let's list just briefly our outcomes. So, our outcomes we get just by tracing along my tree to see what all the possibilities and combinations were. So my first possibility was selecting Anna first, then Brad second. So my first outcome is getting Anna and Brad out of the group of 3. Anna first, Brad second. The next outcome is getting Anna first, Chris second. Now, my next branch of my tree, I'm getting a possibility of Brad first, followed by Anna, Brad first, followed by Chris, and then Chris followed by Anna on my third branch, and following this along. Chris first, Anna second, and then Chris first, Brad second. So that's this particular route down here. So you can see we're taking different paths here. For my first outcome, we're going like this. My second outcome, we are going like this. My third outcome, we are doing this. My fourth, just following along the branches of my tree diagram. And my fifth here, and my sixth here. So I have a total here of 6 outcomes to choose from. And we're going to use this to actually try to answer some questions. So let's go question 1A. I want to find the probability that the selection will contain Anna and Brad. So this is any case where I'm choosing Anna or Brad. The order doesn't really matter because the probability I'm asked to find is just any combination of Anna and Brad. So I can find 1 here and 1 here. These are the only 2 outcomes that satisfy my question. So that means I have a probability of 2 favorable outcomes out of a possible 6, which is my total number of outcomes. And simplifying this, I just get 1/3. That is the answer to question 1. Question 2 is we want to find the probability that Chris is selected. So the probability of selecting Chris at any point in time. So we're just going to count, well, how many times does Chris appear in all of my outcomes? He appears once here, once here, once here, and here. So this probability is going to be 4 out of the possible 6 I have. It's going to be 4 out of 6, which is also going to simplify to 2/3. All right. Now, in this final part, this is where the wording's going to change slightly, but we're going to see what effect this has on the actual question and how we answer it. So here we're looking at the probability that we select Chris or Brad. Okay, so this or is very inclusive. We talked about this when we considered our Venn diagrams, right? We said that saying to find Chris or Brad, we are looking at the cases where we have Chris appearing, Brad appearing, or both of them appearing. So this is anytime you see this or, it's a little bit of a hint that this is quite inclusive or implies Chris, Brad, or both. So we want to see the options here where we get Chris or Brad or both of them. Well, Brad appears here, Chris appears here, Brad appears here, Brad and Chris appear here, Chris appears here, and Brad and Chris appear once more. So we can count a total of 1, 2, 3, 4, 5, 6 possible outcomes. So I'm going to get a fraction of 6 out of a possible 6 outcomes, which gives me 1. This gives me 1 whole. Now, what does this mean, just for a bit of revision in the context of probability? This means, in other words, that this is a certainty that 100%, no matter which way we go up our tree diagram, whether we go this way, or 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 this way, every single time, Brad or Chris or both will be selected. So any way these people get pulled out of the room, there's always going to be a chance that Brad or Chris get selected. Let's even try to visualize it here. Let's say Anna got selected first. No matter which way we look at it, Chris or Brad are going to get selected. One of them will get selected. And every single time, say they were selected first. Well, they've already been selected. This fits our criteria. We are just looking for one case of Chris or Brad getting selected. So it is going to be an absolute certainty that out of these 3 people, either Brad or Chris will get selected. That is why our probability is 1 or 100%. But aside from these little bits of worded, these wordy questions where we have to think about these words at least, or this word or, as long as we have a nice tree diagram set out, so hopefully this video has given you a bit more confidence in approaching these types of tree diagrams, whether we're thinking of with replacement or without replacement. Once we have it here, and it's the same thing I've been saying with all of these videos, you lay it out nicely. Afterwards, you can just read off your outcomes, and it becomes a lot easier to work with these types of questions. And the only thing that's going to get you is some of these worded questions. So when we're asked or at least one, or and. In this case, we're just looking for cases where we had Anna and Brad. So both have to be there. In this case, we could only have one of them, or both. So that is how we can approach tree diagrams and use them to answer probability questions. Thank you so much for joining me in this video, and I'll catch you guys next time.